The nth term test says that if we have an infinite series and this infinite series is convergent, and then the limit of the sequence a sub n is convergent. So here's an example. So what the nth term test says is this. If we have a infinite series like this geometric series of 1/2 to the n, if this infinite series is convergent, and then the sequence 1/2 to the n, this sequence, its limit as n approaches infinity is equal to 0. So that's what the nth term test say. If we have a convergent infinite series, and then the limit of the sequence must go to 0. And here's the proof. And so the nth term test says that given that we have a convergent sequence, so if this infinite series is convergent, then that means it's equal to some real number s, meaning it has to equal to a real number. And we want to show that a sub n, the limit of a sub n as n approaches infinity, is equal to 0. So the sequence of partial sum is so s sub n is the first n terms, a sub 1 plus a sub 2, all the way up to a sub n. The partial sum s sub n minus 1 is the sum of the first n minus 1 terms. So it's a sub 1, a sub 2, all the way up to a sub n minus 1. And now we do s sub n minus s sub n minus 1. So it's all of this minus all of this. And then the only thing that's left is a sub n, because a sub 1 will cancel out with a sub 1, a sub 2 will cancel out with a sub 2, a sub n minus 1 will cancel out with a sub n minus 1. So we end up with a sub n is equal to s sub n minus s sub n minus 1. Now notice that as n approaches infinity, then n minus 1 also approaches infinity. And therefore, if the limit of s sub n is equal to s, then the limit of s sub n minus 1 also equals to s. Because as n approaches infinity, n will approach infinity, n minus 1 will also approach infinity. So we know that a sub n is equal to s sub n minus s sub n minus 1. So the limit of a sub n as n approaches infinity is equal to the limit of s sub n minus the limit of s sub n minus 1 as n approaches infinity. But the limit of s sub n is s, the limit of s sub n minus 1 is also s, so it's equal to 0. And that proves the theorem, the nth term test. And one more time, the nth term test says that if the infinite series converges, then the limit of the sequence must go to 0. And now here are some examples. Here we have the geometric sequence of 0.4 to the n. This is a geometric series. And the first term is 0.4 to the first. And remember that in geometric series, the first term we call it a. The 0.4, that's the common ratio of 0.4. And so this is a geometric series, and r is between negative 1 and 1. The common ratio of 0.4 is between negative 1 and 1. Then we know that the geometric series theorem says that if r is between negative 1 and 1, the infinite series converges to 1 divided by 1 minus r. A is 0.4, r is 0.4, so we have 0.4 divided by 1 minus 0.4, which is 5/3. And so this infinite series, this geometric series, is converges to 5/3. And so we have a convergent series. Now we want to show that the limit of a sub n is equal to 0. So in this case, a sub n is 0.4 to the n. But 0.4, the sequence 0.4 to the n is a geometric sequence. And we know that if we have a geometric sequence and the common ratio is between -1 and 1, then the limit goes to 0. So again, the n-term test says that if the infinite series converges to a real number, in this case it's the real number 5/3, then the limit of the corresponding sequence goes to 0. And here's another example. Here we have the geometric sequence of -0.8 to the n. A is the first term, is -0.8 to the first. The common ratio is -0.8. And this is a geometric series, and r is between -1 and 1. Therefore, the infinite series converges to a divided by 1 minus r. In this case, a is -0.8, r is -0.8. And then simplify, we get -4/9. So this infinite series converges to -4/9. A sub n is the sequence -0.8 to the n. And now we want to show that the limit of the sequence a sub n is equal to 0. -0.8 to the n is a geometric sequence with r between -1 and 1. Because this is a geometric sequence and the ratio, the common ratio is between -1 and 1, then we know that the limit of this sequence must go to 0. And so once again, we have shown that if the infinite series converges to -4/9, then the limit of the sequence, the corresponding sequence, is equal to 0. And here's another example. The sequence, the infinite series, 4 divided by n times n plus 2. This is a telescoping series, and we have shown in an earlier video on telescoping series that this series converges to 3. Meaning this sum right here, this infinite sum, is equal to 3. And now we want to show that the corresponding sequence a sub n has a limit of 0. So a sub n is 4 divided by n times 2. So the limit of a sub n, which is the limit of n divided by 4 divided by n times n plus 2. This is 4, and the bottom will go to infinity, and we get 0. So one more time, we have shown that this series converges to 3, is convergent. Then the limit of the corresponding sequence a sub n is equal to 0. And then here's one more. The infinite series 1 divided by n plus 1 times n plus 2 is a telescoping series and converges to 1/2. And we have shown this in an earlier video on telescoping series. The corresponding a sub n is one sequence is is 1 divided by n plus 1 times n plus 2. The limit of a sub n as n approaches infinity, it'd be 1 divided by infinity, which is 0. So again, we have shown that this sequence is convergent, and therefore the corresponding sequence a sub n, its limit is equal to 0.